diagonal, triangular, and symmetric matrices. I want to give the definitions for all three types here of matrices, look at some of the properties, and then mostly prove some of the consequences, very basic consequences of all three categories. So a diagonal matrix is a square matrix with entries along the main diagonal and zeros elsewhere. If we have a diagonal matrix, it's pretty neat to have it because the terms along the main diagonal would prove beneficial for us later on. You can have differential equations, and you can solve a differential equation by knowing something about eigenvalues, eigenvectors, of which we'll get to in a little while. If you know the eigenvalue and eigenvectors, the matrix is said to be reduced to a diagonal matrix. And the diagonal matrix, the entries along the diagonal matrix, are precisely the eigenvalues. You take those eigenvalues, and they give you the terms when you simplify differential equations where you have that Euler formula, and the solutions are said to be a string of exponential values. Well, so you get c sub 1 times e to some m sub I times x plus c sub 2 times e to the m sub 2 times x, and so on. Well, those m sub 1s, m sub 2s that you have for the differential equation would be the eigenvalues. And if the matrix that you take, you reduce that matrix to find the eigenvalues, you have a matrix that's a diagonal matrix, and the entries on the main diagonal are said to be the eigenvalues. You take those eigenvalues, simply solve the differential equation, and you're done. So the diagonal matrix has great benefits for us in linear algebra and in other courses as well. Triangular matrix. A triangular matrix is said to be a square matrix where you have entries along the main diagonal and entries above the main diagonal with zeros below it. If you have that, we call that an upper triangular matrix. So entries along the main diagonal and above the main diagonal. Zeros below the main diagonal is called an upper triangular matrix. Or the other form of a triangular matrix is the lower triangular, where you have entries along the main diagonal, entries, well, non-zero entries mainly, along the main diagonal, entries below the main diagonal, and then zeros above the main diagonal. So there we call that a lower triangular matrix. Obviously, if I have an upper triangular matrix, take the transpose of it, that would give me a lower triangular matrix, right? And if I have a lower triangular matrix, take its transpose, I get an upper triangular matrix. Well, we can talk about if you have a triangular matrix and if you multiply two triangular matrices, say for example, if I have two upper triangular matrices, then the product, what would you infer the product would be? If it's two upper triangular matrices, then the product would be what? Another upper triangular matrix. Indeed, if I have two lower triangular matrices, you multiply them, then the result would be another lower triangular matrix. What if you have a lower triangular matrix and an upper triangular matrix of the same size, and you multiply them? What do you think you would get? More than likely the zero matrix, right? Well, beautiful. Let's look at here the next theorem that's a property that somewhat categorizes exactly what we just said. So common properties of triangular and diagonal matrices. So we just stated the first one. We just stated the second one, right? Number 3 is important. Number 3, most valuable, most useful to us. A diagonal matrix is invertible if all the entries along the main diagonal are all non-zero. Okay? And the real neat thing about a diagonal matrix is if you have a diagonal matrix, you're looking for the inverse for a diagonal matrix, You just invert the entries along the main diagonal, and you're done. Check the reciprocals, and that gives you the inverse for a diagonal matrix. The inverse of a lower triangular matrix is another lower triangular matrix. The inverse of an upper triangular matrix is another upper triangular matrix. I just stated this property here. The inverse of a diagonal matrix is simply the reciprocals of the entries along the main diagonal. If you have a diagonal matrix and you're asked to find that matrix to the nth power, you simply raise the entries along the main diagonal to that power, and that becomes that matrix raised to that power. So very, very quick, very easy solution if you have a diagonal matrix. The goal in linear algebra, like the second part of this course, or even the first part of this course, where it's the introduction to linear algebra. You have this course is called elementary linear algebra, which is said to be like grade school math, and then you have the introduction to linear algebra. The introduction to linear algebra is where, I prove some of the consequences. The introduction, everything is proven. And in that course, the latter part of the introduction to linear algebra, the goal is to take any matrix, square matrix, and reduce it to its diagonal form, or to try to reduce it to what is called a canonical form, which is, it could be a matrix, we've seen them like a 15 by 15 or 20 by 20, where the matrix can be reduced, where you have subcategories, sub-square matrices within the big matrix, and those subcategories said to be forms of zeros and ones. And then some neat properties you could talk about what that means, and that goes into more of differential equations and dynamical systems. But at any rate, we have to start somewhere. So start here, get a strong foundation, and so if you have to see that information later on, it'll be straightforward. Examples. Classify the matrices as either upper, lower, triangular, or diagonal, and decide by inspection whether the matrix is invertible. Now, when they say inspection, does that mean to do work to solve it? No, it's just inspection. Just look at it, and hopefully you should be able to deduce what is being asked for. So part A, is that upper or lower triangular? It's upper. Is the matrix invertible? Why do you say no? Let's go back up. All right. Part 3 says a triangular matrix is invertible if all the entries along the main diagonal are non-zero. Right? Is part A a diagonal matrix? It's not a diagonal matrix, right? So then the question is it invertible or isn't it not? That's beautiful stuff. Part B, is that upper or lower? It's lower. Is it invertible or not? Part C, this is going to be a good test question for part A and part B. Part C, is that lower, upper, or triangle, or diagonal? It's diagonal. And is it invertible or not? Okay, it is invertible because it's diagonal, all the entries along the main diagonal, or non-zero, and so that's good. Now look at this example. This is here, find a square, find the inverse of a square, and then find the inverse of a to the k. Hmm? So this matrix is diagonal. If it's diagonal, very easy to deal with the properties that we're given. So here, a square is simply, we're going to square the terms along the main diagonal. So we get 1/4 0, 0, 0, 1 9, 0, 0, 0, 1/16. And then you're asked to find the inverse of that. Well, the inverse is just the reciprocal of the terms along the main diagonal. So we get 4, 0, 0, 0, 9, 0, 0, 0, 16. So with that information, what would be the inverse of a to the k, or a to the negative k? What form could you write for that? That's true. But I need some terms inside. Okay. Wouldn't there be an easier way to write that? You can simplify that, and that's k over 9. Right. Wouldn't it just be 2 to the k, 0, 0, 0, 3 to the k, 0, 0, 0, 4 to the k? Right? I mean, the key was this a to the negative 2, right? It was just the first term reciprocated, and it's the 2 squared, right? This is what, 3 squared. That's 4 squared. So then if it's a to the negative k, it has to be what, 2 to the k, 3 to the k, 4 to the k along the main diagonal. Ali, what you said is correct. I think he said, say for example, the first term, he said this is, you said 1/2 to the negative k, and isn't 1/2 the same thing as 2 to the negative 1 to the negative k? Power raised to a power, you multiply the powers, you get what? 2 to the k, right? So it's the same thing if you remember your algebra. Compute the indicated quantity. So what is this equal to? Hmm? 1, 0, 0, 1. And what's your rationale for that? 1, 0. You said 1, 0, 0, 1? What's your rationale for that? That's right. That's right. You got it. All right. Everybody happy with that? Patricia? You good? All right. Determine by inspection whether the matrix is invertible. Do you say yes for this? What about this one? You say no. All right. Symmetric matrices. We're in today with symmetric matrices. Bless you. A square matrix is said to be symmetric if the matrix is equal to its transpose. So if A transpose equal to A, then the matrix is said to be a symmetric matrix. The property, there are 3 that coincide in terms of just basic operations for symmetric matrices. That if you know that A is symmetric, Here we're given that A and B are symmetric matrices of the same size. K is some number. Then A transpose is also symmetric. Interesting. Because how do you know that? Because you're given that A is symmetric. That's the key. I'm given already a symmetric matrix. If I know that A and B are symmetric, then when I add those two matrices together, the result, the sum, is also symmetric. Also, the difference will also be symmetric. And if you multiply a scalar times a symmetric matrix, its result is also symmetric. Do you believe that? No. No, we don't. We don't believe it until we show it. So here, given that A is symmetric, to show that A transpose is symmetric. Well, my question is, do you know what we're actually trying to show? What do we want to show? I mean, what does that mean? Well, you know that. It's given that A is symmetric. If they're saying that A transpose is symmetric, what does that mean? Huh? What equals A? Yes, thank you. Right? If A transpose is symmetric, they're trying to get us to see that A transpose is equal to A. Just want to show that. So that is, show that A transpose is equal to A. Well, here's what we do. We take the transpose of the transpose. Here the question is A transpose symmetric? Do you remember, maybe going back a couple of sections ago, this was a property of a theorem that said that A transpose of the transpose was equal to A, right? Now, by all means, there's the easier way to show that, but here this is just using previous information. Just note that A transpose is equal to A by the fact that A is given to be symmetric. Right? A is given to be symmetric already. Right? Let A and B be symmetric matrices. Part B, or the second part, show here that A, I'm going to put them both together, plus or minus B transpose is equal to A transpose plus or minus B transpose. Right? So if we take this statement, now by definition, this is said to be an proving that. We're trying to prove that. By definition, this is A transpose plus or minus B transpose. By definition. And here, since A is said to be symmetric, or A transpose is also symmetric, even by the previous consequence, that's what we're starting off with. This is A transpose plus or minus B transpose. But A transpose is equal to A plus or minus B transpose is equal to B, and you're done. Here, show that K times A transpose is equal to K times A. Well, this is equal to K to the transpose times the transpose of A. Well, here, since K is a scalar, the transpose of that is still that number. Here, the transpose is in terms of a matrix where I interchange rows and columns. But if I have just one number to interchange that, it still keeps its form. Right? So here, K transpose is just K, and then A transpose, A is said to be symmetric. Since A is symmetric. Now, the product of two symmetric matrices is symmetric if and only if the matrices commute. Have you ever seen that statement before? IFF? If and only if. Do you know what that means? If and only if. If and only if. It's the double implication of a statement. You know how in math and just in our casual conversation, you say, if this, then that, right? So we're familiar with that argument, right? Very basic argument from Greek philosophy. If A, then B. If A, then B. Well, that's the first if. You say if and only if, that means that going from left to right is true. We'll show that. And the other part, and only if, says if I take the conclusion and assume the conclusion to prove the premise. Just want to reverse it. So the if statement says that I go from let's see if we can just give a remark on the if and only if statement. So here, this is if and only if means the first if implies here, P implies Q, and the only if means Q implies P. And so here, this statement, this theorem says you have to prove it twice. You prove it from left to right. Assume that two symmetric matrices, when you multiply them, the result is symmetric, to show that the matrices commute. And then after that, assume that the matrices commute to produce that the product of those two matrices is also said to be symmetric. Right. We'll take up with that on the next day. And for now, that's this. You should be able to do the homework for 1.6 and 1.7. Thank you.